Hello students, welcome to this very interesting video on quantum numbers. In my last lecture we had discussed about the wave mechanical or the quantum model of an atom, which is based upon the fundamental equation of quantum mechanics, that is the Schrodinger's wave equation. The solution of the Schrodinger's wave equation gives us the value of the wave function psi and the corresponding energy states of an electron. But psi is a simple mathematical function and has no physical significance. At the same time, psi square, that represents the intensity of an electron wave, and in terms of Heisenberg's uncertainty principle, gives us the probability of locating an electron at a point within an atom. Thus, we can find a region of space around the nucleus within an atom wherein the probability of locating an electron is as high as 90%. Such a space or such a region around the nucleus within which the probability of locating an electron is very high is what we call as an orbital of an atom. Many different kinds of orbitals are possible within an atom. And these different kinds of orbitals, they differ from each other in their shapes, sizes, and orientation, that is the spatial arrangement around the nucleus. For example, S orbitals are spherical in shape, p orbitals are dumbbell shaped, and the shapes of d and f orbitals are even more complex. Now, to differentiate these different kinds of orbitals from each other, we use a set of numbers which we call as quantum numbers. These quantum numbers have all the information about the location and the energy of electron. So let us, in our today's class, discuss this very interesting topic about quantum numbers. The first quantum number is the principal quantum number n. The principal quantum number n decides the principal shell or the principal energy state of an electron. It is always a positive integer with a value of n being equal to 1 for the first shell around the nucleus, n is equal to 2 for the second shell around the nucleus, n is equal to 3 for the third shell around the nucleus, and so on. It is the principal quantum number which to a large extent decides the energy and the size of an orbital. As the value of n increases, so does the energy of orbital. Understand that it is the principal quantum number n that helps us to explain the main lines in the emission spectrum of hydrogen. These main lines in the emission spectrum correspond to the various electronic jumps that take place from the higher energy levels to the ground state, that is n is equal to 1. Whenever electron jumps from any of the higher energy levels to n is equal to 1, it does so by emitting a radiation of a particular frequency. And this is what gives us the main lines in the emission spectrum of hydrogen. So you can think of these quantum numbers as an address to the location of electron within an atom. See, just as someone who's trying to locate your house should first know that which part of the city do you reside in. In a similar way, the principal shell or the principal quantum number describes the part of an atom where you may locate an electron. But simply knowing which part of the city you stay won't be sufficient to locate your house. In a similar way, we'll need some more information to find the location of an electron within the atom. And this is what takes us to our next quantum number, that is the azimuthal quantum number. The azimuthal quantum number L, also known as the angular momentum or the subsidiary quantum number, describes the sub-energy levels or the subshells within a principal energy level or a principal shell. It is the azimuthal quantum number that helps us to explain the fine lines in the emission spectrum. See, each principal energy level or principal shell has within it a number of subshells. Now, just as the main lines in the emission spectrum, they result due to the jumps that electrons take between the main energy levels. In a similar way, the fine lines in the emission spectrum are because of the smaller jumps that the electrons take in the sub-energy levels. These subshells or sub-energy levels are represented by the azimuthal quantum number L. The azimuthal quantum number L also decides the angular momentum of an electron. In terms of the value of L, the angular momentum can be expressed as under root of L into L plus 1 times h upon 2 pi. But the question is that how many subshells can be there in a given principal shell? So for a given value of n, L can have n values and that range from 0 to n minus 1. Let us understand this. So for example, if I'm talking about the principal shell 2, that is n is equal to 2. So for n is equal to 2, L can have two values. Because look at the statement, what it says, that for a given value of n, L can have n values. So if n is equal to 2, L can have two values. If n is equal to 3, then L can have three values. If n is equal to 4, then L can have four values. And these values of L will range from 0 to n minus 1. So if I'm talking about the principal shell 2, that is n is equal to 2, then the values that L can take are going to be 0 and 1. In a similar way, when I now talk about n is equal to 1, so if n is equal to 1, then L can have only one value and that is equal to 0. If I say n is equal to 3, so how many values can L now take? It will take 3 values. And these 3 values are going to be ranging from 0 to n minus 1. So that is 0, 1 and 2 in this way. Each such value of L corresponds to a particular subshell. The value of L equal to 0 corresponds to S subshell. The value 1 corresponds to subshell P. The value 2 corresponds to the subshell D. Value 3 corresponds to the subshell F. And if the value of L is 4, then you go on further than F, that is G, H, I and so on. So now you've understood that how many subshells can be present in a given principal shell. In a given principal shell, the number of subshells will be equal to the number of values that L can take. And how many values can L take? You know, for a given value of n, L can take n values. And each value of L will then correspond to a particular subshell. So now if I say that for n is equal to 3, the number of possible values that L can take are 0, 1 and 2. It would mean that the third principal shell will have 3 subshells in it. Now what are these 3 subshells? So if the value of L is 0, it means S subshell. If the value of L is 1, it means P subshell. And if the value of L is 2, it means D subshell. So the 3 subshells that are present in the principal shell 3, that is n is equal to 3, the 3 subshells in it are S, P and D. The next thing that you should now know is how are you going to denote these subshells belonging to various principal shells. So let us understand something about the notation of subshells. A subshell always is denoted as NL, where N will represent the number of the principal shell. N will be the number of the principal shell and L here will denote the name of the subshell. The name of the subshell. So let us understand this with an example. For example, n is equal to 3. Now if n is equal to 3, the values that L can take are going to be 0, 1 and 2. L0 will correspond to S, L1 will correspond to P and L2 will correspond to D subshell. Now all of these subshells are belonging to the principal shell 3. So how will you denote them? So you are going to write it as 3S. Now look, this representation 3S is in terms of NL, where N is representing the number, that is the principal shell 3, and L is representing the name of the subshell, that is S. So 3S, it means it is the S subshell belonging to the third principal shell. In a similar way, you will represent the second one as 3P and you will represent the third one as 3D. In a similar way, for example, if you are talking about the principal shell number 4, n is equal to 4. So if n is equal to 4, L can have values 0, 1, 2 and 3, that is from 0 to n minus 1. Now L0 is S subshell, L1 is P subshell, the value of L2 corresponds to D subshell and the value of L3 corresponds to F subshell. But all of these subshells are belonging to the principal shell number 4, and therefore you will represent them by writing 4S, 4P, 4D and 4F. So I hope this makes it very clear that how are you going to give notations to subshells belonging to various principal shells. So here we complete our discussion with the first two quantum numbers. The third quantum number is the magnetic quantum number ML. The magnetic quantum number gives information about the spatial orientation of orbitals within a subshell. In each subshell, the orbitals can have different spatial arrangements. All the possible spatial arrangements or orientations that the orbitals can have within a given subshell are given by the values of ML. Now for a given subshell L, ML can have 2L plus 1 values, and these values are going to range from minus L through 0 to plus L. For example, for L is equal to 1. Now L is equal to 1 corresponds to P subshell. Now for L is equal to 1, ML can have 2L plus 1, that are 3 values. And these 3 values are going to range from minus L through 0 to plus L, that is minus 1, 0 and plus 1. Now since ML here can have 3 values, it means 3 different orientations of orbitals are possible within P subshell. Now these orbitals which belong to P subshell are called P orbitals. It means P orbitals can have 3 different orientations or 3 different kinds of spatial arrangements. Now these 3 different orientations of P orbitals are along the 3 axes, and that's why the 3 P orbitals are represented as Px, Py and Pz. In a similar way, suppose if I say for L is equal to 2. Now L is equal to 2 corresponds to D subshell. How many values can ML have? ML can have, or magnetic quantum number can have, 2L plus 1 values. So 2L plus 1 would mean 2 times 2 plus 1, that is equal to 5 values are possible for ML. Now these 5 values should range from minus L through 0 to plus L. So I'll start moving from minus 2, minus 1 through 0. I'll move to plus L, that is still plus 2. Now as you can see, since 5 different values are possible, it would mean that D subshell can have D orbitals with 5 different orientations. Now these 5 different orientations of D orbitals are represented as dxy, dyz, dzx, dx square minus y square, and the last one is dz square. So these are the 5 different orientations possible for D orbitals. In a similar way, if you say for L is equal to 3, that is F subshell. So how many possible values? 2L plus 1. That are 7 possible values that will range from minus L through 0 to plus L. Now since F subshell can have 7 values for ML, that means F orbitals can have 7 different kinds of spatial arrangements within the F subshell. So these are the 7 F orbitals. Thus, the magnetic quantum number ML gives us all the possible orientations of orbitals within a given subshell. Let us now understand that how many orbitals are possible in a given principal shell. So let us try to find out the number of orbitals which are possible for the principal shell 3, that is n is equal to 3. Now since n is equal to 3, L here can have three values, and these three values are going to range from 0 to n minus 1. See, we should always remember that the values of L can be given from the value of n, and the values of ml can be given from the values of L. Now, since I have got the value of n, I will first determine the possible values of L. And we know that the possible values of L here in this case are going to be L is equal to 0, L is equal to 1, and L is equal to 2. Since there are three possible values of L, it means that there are three subshells which are possible. L0 will correspond to S subshell, L1 will correspond to P subshell, and L2 will correspond to D subshell. Since these subshells are belonging to the principal shell 3, I'll be representing them as 3S, 3P, and 3D. Now I've got all the possible values of L, and from here I will determine the possible values of ML, that are the possible orientations that the orbitals can have within these subshells. For L is equal to 0, ML can have only one value, and in this case the value that ML can take will always be equal to 0. Because remember that ML can have values from minus L through 0 to plus L. But since L is 0, ML can have only one possible value, that is 0, which means that the S subshell can have only one S orbital. For P subshell, the value of L is 1. Since the value of L is 1, ML in this case will have three possible values, and these are minus 1, 0, and plus 1. Since there are three values, it would mean that P subshell will have three P orbitals in it. Lastly, we come to L is equal to 2, which corresponds to D subshell. Now, since L is 2, the possible values of ML can be determined from here, and they are going to range from minus 2 through 0 to plus 2. So these are the possible 5 values of ML. Since there are 5 possible values, the D orbitals here will have got 5 different orientations. So let us now find out the total number of orbitals that are possible. So obviously I can say there is one S orbital that is possible, there are 3 P orbitals, and there are 5 D orbitals here. So if you add all of them, the total number of orbitals here are going to be equal to 9. What was the value of N? The value of N was 3. And what are the possible orbitals in it? So you get the relation, the possible orbitals are N square, and that is equal to 9. So let us try to find out the number of possible orbitals for N is equal to 2. For N is equal to 2, L will have two possible values, that is L is equal to 0 and L is equal to 1. L0 will correspond to S subshell. Since it's belonging to second principal shell, I'll write it as 2S. And L1 will correspond to P subshell, and I'm going to write it as 2P subshell. For L is equal to 0, ML can have only one value, and that will be 0. For L is equal to 1, ML will have three values, and you all know now that these three values will be minus 1, 0, and plus 1. So there will be one S orbital and there will be three P orbitals. So the total number of orbitals are 4, and that is equal to N square. Let us now move on to the last quantum number, and this last quantum number is called the spin quantum number ms. The electron spins about its own axis much in a similar way as the Earth spins around its own axis. Two different kinds of spins of electrons are determined, and these two spins are called the spin energy states for an electron. The two spins are called the spin up state. This is the spin up state and the spin down state. The spin up state is given the quantum number +2, and the spin down state is given the quantum number -1/2. The two spin states can also be represented by arrows. The spin up state is represented by an up arrow, and the spin down state is represented by a down arrow. Thus, to sum up, we have 4 quantum numbers, and these 4 quantum numbers, as I told you, have all the information about the energy and the location of an electron within the atom. The principal quantum number n is that quantum number that will determine the size and to a large extent the energy of the orbital. The azimuthal quantum number will define the subshell of an electron, and for a given value of n, we all now know that the possible subshells are going to be having values from 0 to n minus 1. The magnetic quantum number ml gives us the spatial arrangement of orbitals within a subshell, and the values of ml can be determined from the value of L. ml can have values from minus L through 0 to plus L. Two different spins for electrons are spin up and spin down states, and these are represented by the spin quantum number ms. The spin up state is given the quantum number plus 1 by 2, and the spin down state is given the quantum number minus 1 by 2. So that's it about the quantum numbers. Let us now shift to another interesting topic in today's video, and that is about the energy of the orbitals. Now, the energy of an orbital in hydrogen atom or hydrogen-like species, which are all one electron systems, is solely determined by the value of n. With the increase in the value of n, the energy of an orbital also keeps on increasing. It would mean that 1s is at a lower energy than 2s, but 2s is at the same energy as 2p. The reason is because both of them, 2s and 2p, have the same value of n. But the energy of 2s is equal to 2p but would be less than 3s, which would be equal to 3p, and that would be equal to 3d because they all have the same value of n. We can therefore say that in all those single electron systems which are similar to hydrogen, the energy of any orbital or subshell is solely determined by the value of n. But when we look at multi-electron systems, we come to know that for a multi-electron system that has more than one electron in it, the value of energy is determined both by n as well as L. There is a simple rule to determine the energy of an orbital here or a subshell here, and that is n plus L rule. For a subshell that has a greater value of n plus L would also be at a greater energy. Let us understand this with one example. So let us take two subshells, 3s and the other one is 2s. What will be the value of n plus L for 3s? So n is 3 and for s the value of L is 0. So it would be 3 plus 0. In this case it is going to be 2 plus 0. So for 3s the value of n plus L is 3, and for 2s the value of n plus L is going to be 2. Now since 3s has a greater value of n plus L, I will therefore say that 3s is at a greater energy compared to 2s. But sometimes you may get the same value of n plus L. Let us understand this. Once again I am going to compare 3s, but this time I will compare it with 2p. Now for 3s, as we know, the value of n plus L will be 3 plus 0, and that is equal to 3. And for 2p, n is 2, and for p subshell the value of L is 1. So it would be 2 plus 1, and that is again equal to 3. Now both 3s as well as 2p have the same value of n plus L. In such a case, where you get the same value of n plus L, the subshell with a greater value of n would be at a greater energy. This would mean 3s is greater than 2p. Let us try to compare the value of n plus L for 3d and 4s. Now for 3d the value of n is 3, and for d subshell the value of L is 2. So in this case it would be 3 plus 2, and that is equal to 5. For 4s, the value of n is 4, and for s subshell the value of L is 0. So that is 4 plus 0, and that is equal to 4. Now you see 3d is a subshell of a lower principal shell, because 4s is a subshell of a higher principal shell, that is 4th shell, and 3d is a subshell of the 3rd principal shell. But since 3d has a greater value of n plus L, I will say 3d is at a greater energy than 4s. So in multi-electron systems, it will happen that the subshells belonging to a lower principal shell may sometimes be at a higher energy than a subshell belonging to a higher principal shell. So now I know you all want to know why is it so. To get the answer why is it so, let us take into consideration following facts. Number 1, see, when we are talking about hydrogen atom or any single electron system, there is only one kind of interaction that is present here, and that is an attractive interaction between the positively charged nucleus and the negatively charged electron. So, since there is only one electron, there is only one kind of interaction, and that is attractive interaction between the positive nucleus and the negatively charged electron. But when we talk about any multi-electron system, then along with the attractive interaction that is present in between the electrons and the nucleus, there is also a repulsive interaction that now comes into play between the inner electrons or the electrons in the inner orbits and the electrons in the outer orbits. So along with attractive interaction, there is also a repulsive interaction that is now present in between electrons, because now it has more than one electron. One another important thing to understand over here, let us have a look at it, is what we call as the shielding effect. So let us say here we have the electron of interest, and what I'm explaining you, so I'm explaining you one very interesting thing, and we call this as the shielding effect. Okay, so here we have our electron of interest. Now see, there are some electrons which are present in the inner orbits, and there are some electrons which are present in the outer orbits from our electron of interest. But for those electrons which are present in the inner orbits, these electrons are going to shield my electron of interest from the positive charge of the nucleus. Now, since my electron of interest would be shielded up by the inner electrons, these inner electrons are going to cancel the positive charge of the nucleus that is acting on my electron of interest, because the electrons of the inner orbits would consume some positive charge, will overcome some positive charge of nucleus before that charge reaches the electron of interest. Therefore, the net charge of the nucleus that reaches up to my electron of interest is not the actual charge of the nucleus, because some of that positive charge has already been consumed by the electrons which were present in the inner orbits. Now, the nuclear charge that is experienced by my electron of interest is called the effective nuclear charge, and that is called Z effective. Now, the interesting fact is that all the subshells do not shield to the same extent. Those subshells which are very close to the nucleus, those subshells which are more penetrated towards the nucleus, those subshells which are more concentrated onto the nucleus will give you a better shielding effect. And it is observed over here that the S subshell or the S orbital, being spherical in shape, it is more penetrated or more concentrated towards the nucleus. So with the help of an example, let us compare the 2s subshell and let us compare it with 2p. Now since 2s, as you can see here, is spherical in shape, this 2s subshell or orbital which is spherical in shape will give you a better shielding effect, because it is more focused, more concentrated, more penetrated towards the nucleus. And you look at the p subshells, or you look at these p orbitals. These p orbitals, as you can see here, are more diffused. They are far away from the nucleus. They are not as concentrated on the nucleus as my s orbital. Now, since the p orbitals are more diffused, more scattered away from the nucleus, they cannot give you better shielding as that can be given by the s orbitals or the s subshell. So, as far as I can talk about the shielding effect of various subshells, I will say that the shielding effect of S is greater than the shielding effect of P. In a similar way, when you look at d orbitals, they are even more diffused. And since the d orbitals are even more diffused, the shielding effect of d would be less than that of p orbitals. So I will say S produces a greater shielding than P, P subshell gives you a better shielding than D, and the least shielding is given by F subshell or F orbitals. Now, since the S subshell is the most concentrated towards the nucleus, the electrons in the S subshell, I'll call them the S electrons, would be the most strongly attracted electrons by the nucleus. And this is what takes the S subshell to the lowest energy. Now, for those electrons which are present here in the P subshell, we'll call them the P electrons. We can say that the P electrons would be shielded by the S electrons, because the S subshell is more focused, more concentrated towards the nucleus than P. So when you have electron in P subshell, these P electrons are now going to be shielded by the electrons present in S orbitals. So I'll say P electrons are shielded by S electrons. Therefore, the effective nuclear charge on P electrons would decrease, and this would take P subshell at a higher energy as compared to the S subshell. So I'll therefore conclude that S subshell is at a lower energy than the P subshell. If you continue the same logic, you will therefore say that when you talk about D electrons, that are electrons which are present in D subshell. So as I told you that the D orbitals are even more scattered, even more farther away from the nucleus. So the D electrons would now be shielded by both S as well as P electrons. Therefore, the effective nuclear charge on D electrons would further decrease, and this would take D subshell at a higher energy than P. So again, the order is S subshell at a lower energy than P, P at a lower energy than D, and D subshell will be at a lower energy than F. All of this is true for a multi-electron system. But when you are talking about a single electron system like hydrogen, now whether the electron is in S, P, D or F, there can be no shielding. Since there can be no shielding, I will always say that for a single electron system like hydrogen, or I'll simply write this, that for hydrogen like systems or species, there can be no shielding because there is only one electron. And if there is no shielding, then the energy depends only on the value of N, which would mean that Ns will be equal to Np, will be equal to Nd, will be equal to Nf. That is, only when the value of N will change, the energy of the subshell or the orbital will change. But for multi-electron system, we know that Ns is at a lower energy than Np. Why? Because the P electrons are shielded by S electrons. And we know that Np is at a lower energy than Nd. Why? Because the D electrons are shielded by both S and P electrons. And finally, Nd is at a lower energy than Nf. So, the different subshells belonging to the same principal shell are now not at same energy, because it also will now depend on that in which subshell the electron is present. If the electron is present in P subshell, it will be at a higher energy as compared to when it is present in S subshell. So therefore we say that energy is now decided by both N as well as L. And we have a simple rule. That simple rule is N plus L rule. The reason for this, which I just explained you, is the shielding effect. So that's it for the today's video.